this computer. All right, good. We're going. All right, so welcome back. Hope you had a nice spring break. And what I'd like to do today is to kind of finish up one topic from chapter 4 that I didn't have a chance to get to until now. And that is the issue of what are called dilutions. The third experiment that you do in the course is what's called a titration. And a titration is a type of experiment that almost always involves a dilution calculation. So I'm going to talk about dilutions today, and then we'll get into the next primary topic section, which is thermochemistry. So, and that's, it's just a lengthy topic, so we'll get into that next. But for now, let's talk about dilutions. And this is in section 4.5. And let me give you a little picture of what we're talking about to begin with, okay? So the idea is this. Imagine that you want to make some kind of solution. I like to use the analogy of Kool-Aid if you're making a Kool-Aid solution. Different people use different formulas for Kool-Aid. So one person might take a cup of water, a cup or 2 cups, a pint of water, and add 1 scoop of Kool-Aid mix to it. Other people might do 2, other people might do 3. So depending on how much of the Kool-Aid mix you put into the water, you're going to have a different concentration of sugar, a different concentration of tartness, of the sourness, a different concentration of the grape flavor or the cherry flavor. You're going to be varying the concentration. And so you're making a mixture, right? You're taking all of these solid materials, the sugar, which is sucrose, and all the other thing, the tartness in there and the flavors, and you're varying the concentration. So we can change concentrations of solutions. We do it all the time, right? And so the dilutions is a calculation that we do in chemistry. And it's used a lot in pharmacy, in the pharmaceutical field, because you may need to make solutions that have either higher or lower concentrations depending on the needs of the patient. Okay, so let's take a look at an example of what I mean by that. Typically, the way these problems start is you have some sort of device, a piece of glassware. I didn't draw that very well. Let me try that again. Hey, that's a little better. More like a triangle. Okay, so we'll call this device a volumetric flask. A volumetric flask typically has a little ring on the neck, I guess it's called the stem, on the stem of the volumetric flask. And that ring is there. It's like etched in or painted on. Typically it's etched in and then they put some paint in it on the etching. It's there to indicate how much liquid you need to put in to fill up to that ring. So let's say, for example, that this is a 100 ml. Typically they'll etch that on there as well. They'll write that on there. So that means that if you fill the liquid right up to that ring, that would be 100 milliliters. And typically volumetric flasks, they're only meant for one measurement, meaning only 100. We wouldn't use it if we needed to measure 50. We wouldn't use it if we needed to measure 70. We only use it for one number, which is that number that's printed on there. And so there's only one kind of marking on the whole thing, which is right there with that ring. And that's your 100 ml mark. We call it a mark. or a marking. All right. So then what we would do is we would have some mixture in there, right? So it could be the Kool-Aid, it could be something else, it could be hydrochloric acid solution, some mixture. And then what we would do is we would use a device, which is typically what's called a pipette. So we have this little device called a pipette. And then the pipette has some sort of way of pulling a vacuum. So one way to pull a vacuum is just have like a little tube. If you've ever seen these little tubes used typically on little babies to suction stuff out of their nose if their noses get, if their sinuses are filled with mucus, then what you do is you stick this little thing up their nose and you suction it out. So the same idea, you just use one of those, you stick it into here and then suction out some of this liquid. You stick it in there and pull that liquid out, and then you put it into another container. So that other container could also be a volumetric flask. It could be something else as well. I'll draw this one a little bit differently. They're not always exactly the same shape. And let's say this one is also 100 ml. Okay, so right there, see that ring up there, that's 100 ml. It's a little bit different shape, but that's fine. They cut, depending on who makes it, it might have a different shape. So imagine that what I did was I took out just some of this liquid. Let's say we just took out 10 milliliters of it. So I'll write the 10 ml here. Okay, so we're just pulling 10 out of the 100, right? Only 10% of that is in there. And then we pour that 10 into here. Okay, since it's only 10 milliliters, it's only going to fill up the little bit at the bottom. And then we fill it up with water. And it goes up to 100. What we've done is what's called a 10-to-1 dilution, right? We took 10 milliliters of the original solution and diluted it with about 90 mil. It's not exactly 90 milliliters of water, but around 90 to up to 100. And we've diluted it by a factor of 10, right? That's called a 10-to-1 dilution. And so this would allow us to quantify things. So typically, the solution you're starting off with, this is the higher concentration solution. And this is the lower concentration, right? Because you added water. They have names. So this one's typically called the stock solution. You know, in chemistry, we have something called a stock room. So you go to the stock room, that's where all of the materials are kept, all the chemicals are kept that you're going to use. So we stock our solution there. So it's called a stock solution. It's the one that's more concentrated. And then over here, it's less concentrated, right? So it's more diluted. So we call this the dilute solution. Okay. And notice I gave numbers here, right? Like we started off with 100 milliliters, we took 10 of it out, and then we diluted it with water up to 100. That allows us to do some calculations. And here's the very simple formula you can use for these calculations. It's really cool. It's called the dilution formula. And essentially what it says is the concentration of the stock. So I'll write CS for stock, right? So concentration of the stock times the volume of the stock. Now, be careful. The volume here is not this total volume. It's the volume that you take out, because we're going to use it to figure out what the concentration over here is. So we don't really care how much is in here. We only care how much we take out, okay? So that volume of the stock is not the total, it's the volume you take out. That product is equal to the concentration of your dilute solution times the total volume of your dilute solution. So this entire 100 milliliters, okay? So just be careful with the numbers. But what that does is it allows you to determine the relationship between the stock and the dilute solutions. Now, Most likely, when we do these calculations, our concentration units are going to be in moles per liter, molarity. We talked about that before the break. So often it's written as M for molarity of the stock times the volume of the stock equals the molarity of the dilute times the volume of the dilute. So this is just an alternate way of representing it using different symbols. So this is saying concentration. And the reason that we might write it that way is that different people use different concentration units. In this course, we use molarity, but you might use something called molality. You might use something called mass percent. You might use something called volume, mass volume percent. There's different units that are used out there. So what I'm pointing out is that it's general. You can use it, whatever the concentration units you have, you can use it. But if you're using molarity, we just might go ahead and just put M in there for molarity. It's also common to, instead of actually writing out as S for stock and D for dilute, just saying initial and final, right? The initial situation is over here, and then your final situation is over there. The dilute solution is the final. So you could also write it as M initial times V initial equals M final times V final. So it's also written that way. And even one more, we might do 1, 2. So we might just use numbers. 1 would be the initial and 2 would be the final. So you might also see it this way. M1 times V1 equals M2 times V2. And it doesn't really matter what notation you want to use. The point is, whatever the concentration is in the stock times the volume that you take out, this is the volume you take out, is equal to the concentration of the dilute solution times the total volume of that dilute solution. So in this case, VD or VF or V2 would be 100 ml. And the amount that you took out would be 10 ml. So we took out 10 and then we added 90 to get up to 100 for water. Okay, so let me show you an example. It's pretty simple. Let me escape here and we'll bring up an example. Okay, in this one, this is, again, on Alex, they just call it dilution. It says that you have a chemist, and the chemist makes 900 milliliters of aluminum chloride solution, AlCl3. This is called, he called it a working solution by adding distilled water to 150 ml of a 2.87 molar stock solution in water. And then it says, calculate the concentration of the working solution. Okay, now in this particular, for whatever reason, Alex decided, the people that put these problems together decided to call it a working solution as opposed to a dilute solution. So people change the words over time. The working solution is the same thing as the dilute solution. Okay, it's the solution you're going to work with. The stock solution is what you start off with. Okay, so let's just go ahead and identify things. Now remember, I'm going to use this, I'm going to use M for molarity. So I'm going to do M1 times V1 equals M2 times V2. We'll use that one. Okay, so what it says is a chemist makes 900 milliliters of the working solution. Okay, so there's your first piece of information. The working solution is the dilute solution. So that means, I'm just going to label it over here. The first piece of information they give you is that V2 is 900 ml. Okay, the working solution is V2. The next piece of information is it says that you're going to add water to 150 ml of a 2.87 molar. Remember, capital M means molar. That's a unit of concentration, moles per liter, of stock solution, okay? So there's two numbers given there that go together, right? It's 150 milliliters of 2.87 molar stock solution. Okay, well, stock is M1 and V1. So M1 is the stock, so that's 2.87 molar. And then how much of that stock solution is V1? And it says it's 150 ml. Okay, so let me show you a little picture of what happened here. The stock solution, just to make the drawings a little simpler, I'll take the stock solution here as a beaker instead of a flask. So what they did was they took out 150 ml. Remember, the volume that you're concerned about with the stock is not how much stock you start off with, but just how much you take out. And then it's put into some container where the total volume is 900 ml. Okay, so you put the 150 in of the stock, and then you add water until the total is 900. Now, you can do the arithmetic. You can tell that the water volume would be 900 minus 150, right? If you have 150 of the stock and your total volume is 900, it comes out to 750. But generally, we don't want to know that number. And the reason that number is unimportant is because it turns out when you mix things together, volumes are not exactly additive. It's kind of interesting. When you take a stock solution and you add water to it, you would say, hey, if I took 150 of this and 750 of that, that'll give me 900. But what happens is the ions or the molecules that are in the water, they interact with the water that you add, and it changes the volume a little bit. So if you really want to be very precise and accurate about it, you can't just say add one. If it was just pure water, you could add 150 to 750 and that would give you 900. But if it's a solution, diluting it actually changes the amounts of interactions and the volume changes a little bit. Typically it goes down a tiny bit. So what you do is you say, okay, I'll put 150 in, but then I'll just add enough water to get up to 900 and stop at the 900 mark. You don't add 750. If you added 750, you'd be pretty close, but you wouldn't be exact. Okay, so for that reason, they don't generally ask you how much water do you add. Okay, they want to know what's the total volume or how much of the stock did you have to add in order to get these concentrations. So we've got three numbers. There's only one that we don't have, and that's what they're asking for, right? They're asking for the concentration of the working solution, which is M2. All right, so that's pretty straightforward. Now it's just a matter of going through the algebra. Let me go ahead and erase these pictures. We don't need these pictures for this. Okay. So here's our starting formula, our dilution equation. We want to know M2. So pretty straightforward. If you want to find M2, you divide both sides by V2. Because if you divide the right side by V2, you get 1 and you're left with M2. So that means M1 times V1 over V2 is equal to M2. You'll do a lot of this when we get to chapter 10 when we deal with the gas laws. Gas laws are all about these sorts of equations. Something times something equals something times something. Okay, so now it's just a matter of putting the numbers in. So M1 we said was 2.87. Now, I'm going to write molarity just to remind ourselves. Molarity, it's easy to forget this, is moles divided by liters. Capital M means moles divided by liters. It's actually 2 units together. So there's M1. It's the number of moles in 1 liter of something. So if I had 1 liter of this stock solution, I'd have 2.87 moles of aluminum chloride. You're going to multiply that by V1. V1 was 150 milliliters. And then you're going to divide that by V2, which was 900 ml. Now, think about it for a moment. If you're diluting something, the concentration should be lower at the end than it is at the beginning, right? You don't add water to Kool-Aid and make it more concentrated. You add water to make it more dilute, all right? So the final concentration here should be lower than it started off at. It started at 2.87. Take a look at the arithmetic, right? If you're multiplying it by a number 150 and then dividing it by 900, it's going to give you a smaller number because 150 over 900 is less than 1. So there we go. Okay. So now let's just go ahead and do a little calculation here. Let me do it over here. 2.87. I'm going to do with my little calculator. Here it is. Oh, shoot. It's kind of crazy. Okay. 2.87 times 150 over 900. Oops. 2.87 times 150 over 900. Looks like it comes out to about 0.478. And then what about the units going to be? We're looking for molarity, so it should be molarity units, which is moles per liter. Let's see if it worked out. Milliliters divided by milliliters. Okay, that's good. So we're left with moles per liter. So it would be moles per liter. Now, chemists will often write this. If I were writing this on a bottle and labeling what the concentration of the solution is, I would typically just put a capital M. I wouldn't write out moles per liter. I would just write capital M. And the way you pronounce that is molar. So we would say that this working solution or dilute solution is 0.478 molar is the way you would pronounce it. It's a molar solution, but molar means moles per liter, okay? We don't have a similar name for density. So if you think about it, like if I said the density of water is, 1 gram per milliliter. We don't have a name for that. We just call it grams per milliliter. But if we gave a name to it, we might call it, I don't know, masser, right? And so you have molar, which is moles per liter. If you had grams per milliliter, you might call it masser. So we'd say it's a 1.0 masser, but that never developed historically. So we don't have that name. But for molarity, we do have a name. It's called molar, okay? Let me see if there's one that's any kind of different. Okay, that's pretty much the same. Okay, there's one that's a little bit different. Let me show you one more. Okay. So in this particular example, they say, look, you want to dilute. The chemist wants to dilute a solution. And then they tell you some information about the solution. They say it's 83.3 milliliters of 6.54 molar aqueous silver nitrate. Until the concentration, it's kind of odd wording here, falls to 2.00 molar. Okay, 2.00 molar, okay? And then what it says he'll do this by adding distilled water. So it says calculate the final volume. And then a little information about rounding it, okay? Oops. Be careful, I click on the buttons. Okay, so we're gonna dilute a solution. So let me draw a little picture. I find it helpful for me when I do these problems to draw a little picture, just so you kind of see what's happening. We have a solution already. Here's the solution that we have. We have 83.3 milliliters. Okay, so, you know, you wouldn't have a device that measures out 83.3. I don't know, you know, why they pick these numbers, but essentially what they're telling you is the volume of the solution, you know what it is, and it's 83.3 ml. And then they tell you that the concentration, the molarity, is 6.54 molar. Okay, now, you know, it's silver nitrate, AgNO3. It says it's aqueous, it's dissolved in water, it's a solution, okay? When you move a substance like this into another container, you're moving a mixture, right? You're moving the water, but you're also moving everything that's dissolved in the water. So for this particular problem, it's silver nitrate dissolved in water. You're moving that whole thing. So it says we're going to take that whole 83.3. So see how that's a little different than the previous one. In that one, they said, you know, you take out 150 of it. Here, we're taking the whole thing. We're taking the whole 83.3. And we're going to dilute it by adding water. So one way to imagine that is we're going to add water to this 83.3. So here's your 83.3, right? The one that we moved in there. And then we're going to add water. But now, instead of telling us how much water we're going to add or telling us what the volume is, they don't tell us what the volume is. They just say you're going to add water. But they tell us that once you make it, once you make this mixture, the concentration is now 2.00. And they ask us for the volume. And my point about this question is that it's no more difficult than the one we just did. It's really just, it's just how you manipulate this equation. We have this dilution equation, right? M1 times V1 equals M2 times V2, okay? So in this particular question, they asked for the final volume. So they really just want to know what this whole volume is, okay? So that would be V2. Remember, the whole volume that you end up with in the working solution or the dilute solution, that's V2, okay, the whole volume. So that means our dilute solution or our working solution is M2. So we've got both of these. And I'm sorry, we don't have V2. We're asked for that. So let me erase that. And then on the other side, how much did we put in? 83.3 milliliters. So that's M1. I mean, V1. And what was its concentration? 6.54. Excuse me. So that's M2. So we have M1. We have M1. We have V1. We have M2. And then we're just asked for V2. Okay. So if they're asking you for the total volume here, the final volume, that would be V2, okay? So let's take a look at how we go about this. It's just the algebra. We know M1, we know V1, we know M2, we want to find V2. Just divide both sides by M2. So those are now gone. So now we have M1, just to write it one more time, times V1 over M2, and that's going to be V2. Okay, so then we just need to put the numbers in. Let me erase all this drawing over here. Okay, so same formula, same equation. So I'm gonna move it all the way up here. Okay, so our M1 is 6.54. Again, I'm going to write the units in explicitly. Moles divided by liters. times V1, that's 83.3 ml. And then we're going to divide that by M2. And M2 was 2.00 moles per liter. Okay, oh, I guess I'll put that in parentheses too. And that's going to be your V2. Okay, so look at the units, moles divided by liters, moles divided by liters, they divide out. And we're going to be left with milliliters. Okay, so V2 is going to be some number of milliliters. So it's 6.54. 6.54 times 83.3 divided by, oops, I'm sorry, I made a mistake there. Let me come back here. Right, 6.54 times 83.3 divided by 2.0. Okay. I'm having to switch this. 6.54, oh, there it is. 6.54 times 83.3 divided by 2, and you get 272. And then our units are milliliters. Okay. So let's see if that makes sense. Essentially what we did, I'm going to redraw it here just so you can sort of see. We took 83.3 ml, and it was at 6.54 molar. We added water to it, right? And we added water such that it was 2.0 molar. And now what we're claiming is our total volume is 272 ml. Now, if you think about it, essentially, let me go through just sort of estimating. This is a little skill that can sometimes help. First of all, we know the total volume's got to be larger than it started off as, right? If you're diluting something, you're adding water. So if we had done this problem and we came out with a volume of 40 milliliters, we would know that's wrong, right? Because if you're starting at 6.54 molar and you're adding water to make it 2.0 molar, the volume has to be larger at the end than it started off with, right? If you add water to Kool-Aid, that's what dilutes it. So the volume has to be more than 83.3 milliliters. So that's good that it was 272. But now let's think a little bit about how this works. I'm going to use just really round numbers just to do counting. And so the round numbers I'm going to use is I'm going to round this to 6 molar. And I'm going to round this to 80 milliliters. You see why I'm doing that? Because those are really easier numbers to kind of do in your head than 83.3. So imagine I added another 80 milliliters. Okay. That would be doubling the volume, right? So what would happen is your molarity, since you have 160 milliliters, would go down by 2. If you double the water, the molarity will go down by a factor of 2. So the molarity would now be 3 molar. Okay. Now imagine instead of adding 80, you add another 80. So you add 80 plus 80 plus 80, right? So you're adding 80 twice to the original. So now you'd have 240. What would happen is the molarity would go down from 6 down to around 2, because now your final volume is 3 times what it started off as. So your concentration would go down by a factor of 3. So now you go down to about 2 molar. Okay, so a total volume of 272 kind of makes sense. It sort of works out mathematically. Okay, so that's a dilution there. I just want to point out, if they ever did ask you how much water you added, that's actually not maybe the best question to ask, because as I said, when you dilute things, the volumes change a little bit. But roughly speaking, it would be your total volume, 272, minus what you started off with, 83.3. So whatever that works out to, 190 or something like that. That would roughly be what you had to add. But in general, you wouldn't ask that question because, again, the volumes change when you dilute things. Okay, so the more proper question is, what's the total volume? Okay, so that's dilutions. You don't really have to do much more than that. The textbook has a little topic called serial dilutions. I'll just make a real quick mention about that. Imagine we had something that was really very high concentration. Let's say it was 11 molar. That's pretty high concentration. It's hard to get things to dissolve into water at concentrations higher than that. And let's say we wanted to go all the way to, 0.0011 molar. That's a big dilution, right? We're going from 11 down to 0.0011. That's not easy to do in one step, because what would happen, you'd have to take out a tiny little bit of volume and then add it to a lot of water. So typically what we do is we do what are called serial dilutions. And I'm not going to have you do any calculations with this, although your textbook has them. Alex doesn't, I didn't assign any of those. What you would do is you would dilute 11 molar down to something manageable like 0.11. Okay, so you do step one. So you might take 10 milliliters and dilute it to 1,000 milliliters. Okay, that would work. Then you would do another dilution. You do a second dilution. You take this 0.11 molar and you dilute it to 0.0011 molar. So again, you might take 10 mLs of this and dilute it to a liter, 1,000 milliliters. And then you might take 10 milliliters of that and dilute it to 1,000 milliliters. So you do it sequentially as a couple steps. And by doing that, it's more work, right? You're doing more dilutions, but by doing that, you can now get down to pretty low concentrations. Okay, that's called serial dilution. And we have to do that sometimes because our changes in concentration can be pretty big. Okay. All right, so that's pretty much it for chapter 4. It was a lot of material, right? We had kind of our discussion of how water interacts with solute particles, with ionic compounds and sugars and alcohols. Then we had to go through our precipitation rules, and then our redox and our oxidation numbers, writing the half reactions. And then we got into our molarity, moles per liter, and then dilutions. So not a bad idea as you get prepared for exam 2 to do those practice exams, right? You can do the practice exam as many times as you want. Practice it a couple of times just so that you get ready for the exam, okay? And not to mention the fact that it's been a spring break and many people don't work very much during spring break, okay? All right, so what I would like to do now is to get to our next topic, which is chapter 5. And chapter 5 is a discussion. Oh, just to point out, after you complete chapter 4, you may need to do what they call the knowledge check. So before it allows you to start working on chapter 5, you'll need to do kind of a review of chapter 3 and 4. So try to take that seriously when you do it, because what happens is if you do that knowledge check and you get all, you just skip through the chapter 3 and say, I don't know how to do it, it's going to start bringing those problems back into your assignments, and that's going to slow you down. So do the knowledge check to the best of your ability. And the idea behind the knowledge check is that by the end of the course, we want you to be able to do these molarity calculations. We want you to be able to balance equations and stuff. We don't want you to do it for 2 weeks and then not know how to do it. So there are 2 of these knowledge checks in the course. One is after chapter 4 and the other one's after chapter 10. So be careful with that, okay? So let's get into 5. So chapter 5 is called Thermochemistry. And thermochemistry is really the issue of energy, okay? Chemical changes involve rearrangement of atoms, right? So when we talk about chemical changes, we're really talking about the rearrangement of atoms. So for example, if I take this equation here, I'm going to balance it. Okay. This is a pretty famous reaction. This is the burning of natural gas. So if you have a gas stove, this is the reaction that's occurring when you get the blue flame out of it. So methane reacts with oxygen to form carbon dioxide and water. So what's happening? Well, pretty simple. You have a rearrangement of atoms occurring. I'm not saying the process is simple, but the actual net change is pretty simple. So you have two oxygen molecules. I'll write double bonds. And then you have a carbon dioxide. And then you have two waters. So water, right? Okay, what happened here? The atoms rearranged. That's what a chemical reaction is. It's just a rearrangement of the atoms. Here, the carbon is attached to hydrogen atoms. Here, the carbon is attached to oxygen atoms. That's really what combustion is. The oxygen atoms, they just rip the carbon away from the hydrogens. They're very reactive atoms, oxygen is. And they attack the carbon, but they also attack the hydrogen. So oxygen likes to react with almost everything except for maybe gold or helium. So these oxygen atoms will just rip apart the carbon-hydrogen bonds, and now you've rearranged the atoms. So now the carbon is with the oxygens and the hydrogens are with the oxygens. That's a chemical reaction. But one aspect of a chemical reaction that's significant, and that's what we're going to talk about in chapter 5, is there's also energy changes that occur. So a chemical reaction involves a rearrangement of atoms. That's a chemical change. But it also involves energy changes. And energy is something that we've got to talk about because the reason that we use natural gas on a stove is because we want heat, right? We want to boil water. We want to cook SpaghettiOs. We want to use the energy that's in that chemical substance, methane and oxygen, in order to do the sort of work that we want to do. For an automobile, we want to use the gasoline, the fuel, and the oxygen that's in air to combust that fuel in order to move that automobile from one spot to another. So it turns out that from a chemical perspective, there's two forms of energy that we like to talk about. One is called heat. So that would be cooking something, right? But the other is work. In a sense, we're burning fuel in an automobile, but we're not doing it to get heat. We don't want the heat, although you can use a little bit of it to heat up the car when you're driving in the winter. We want to move that car. We want to move the bus. We want to move that jet that's flying across the country, right? That's not about heat. It's really about doing what we call work. Moving an object from one spot to another requires work, just like a muscle, right? You contract these little parts of a muscle fiber, and the contraction is doing mechanical work. We call that work. All right. So let's take a look. I'm going to try to look at a problem so that we can kind of get into it, but oops. But there's a lot of theory behind this as well. So let me talk a little bit about that as well. Okay. The first thing I'd like to do is to talk about potential versus kinetic energy. Okay, potential versus kinetic. Potential energy okay, now the symbol for potential energy, there's different symbols we could use. I'm going to use a V for potential energy, okay? Potential energy is the energy associated with position. If you want to think of it this way, we could call it location. Now, it's really a relationship between two or more objects. So for example, the moon has a position relative to the Earth, and there's energy in that relationship due to gravity, right? Gravity is the actual cause of the energy, but there's a relationship between the moon and the Earth based on the position of the moon. And that energy that's based on the position is called potential energy. So let's go back one step, which is to ask the question, what is energy? And it's not a simple question to answer because it's actually a somewhat abstract concept. It's actually something that material matter has. We know it has it, but it's not that easy to explain exactly what it is, right? So here's the way, one way to deal with it is, energy is the capacity to do work. Now, I'm going to make the claim that that's actually what we would call a circular argument, because work is energy. So essentially what we're saying is that energy is the ability to have energy. That's not really a very good definition, right? And the reason for it is because, again, like, it's not easy to actually answer what exactly energy is. We kind of know what it is by experiencing it, but it's hard to come up with a very satisfactory definition. But we do know what work is. Work is when you move something against a force. So for example, if I take this pencil and I move it up, I know that it takes energy to do that, right? Now, why does it take energy? The Earth is pulling down on that pencil. It's also pulling down on my arm, right? Gravity. So I have to do work against gravity. But if I can move that pencil or my hand, even if, to be honest with you, even if I don't have a pencil, it still takes work to move my hand because my hand has weight. That requires energy. Work is this movement that we're doing against gravity. Okay, so that's what work is. So if I say that energy is the capacity or the ability to do work, really what I'm saying is, if whatever I'm calling energy allows me to do this, to fight gravity and move something against gravity, then that's definitely energy, right? So one type of energy is potential energy. And the reason we call it potential is because we don't see it working. We don't see it doing it. It's kind of invisible. Our eyes don't see it happening. So when you look up at the moon, you don't see that it has potential energy because you just see this object just sort of sitting there. But the Earth and the moon are interacting with each other in some way, so we would say that they have energy. Now imagine that for some reason the moon crashed into the Earth. You would see the energy at work then, right? A meteor hitting the Earth, you see an explosion, you can see that energy. That energy that you can see happening is generally, we call that kinetic energy. The energy that you can't really see is potential energy. So a battery, look at a battery, you don't see anything happening there, it's kind of invisible, but it has energy in it, and we call that potential energy. Once you're using that battery, electrons are moving through the circuit and you're hearing sound come out of a speaker, or you're seeing images going across the screen, or the phone is vibrating. Now you have your kinetic energy. Now you can see that something is happening. That's kinetic. The invisible energy is just based on the position. So in chemistry, this is important. And here's why potential energy is important. There's the energy of the moon and the Earth. That's a potential energy. But there's also the energy of a nucleus of an atom, right? The nucleus of an atom is positively charged, electrical charge. But the other particle in an atom is the electron. And this one has negative charge. And what we know is that when you take particles that have electrical charges, they interact with each other and have an energy, a potential energy between them. So we would claim that there is potential energy between the nucleus. So that's V, right? There's potential energy between the nucleus of an atom and the electron. Could be more than one electron, obviously. Between the electrons and that nucleus, there's a potential energy. So if the distance changes, the potential energy changes. So that's an important aspect of it, which is if the distance changes, the potential energy changes. So what happens in an atom is you have a nucleus, and then you have more than one electron. So you might have an electron here, you might have an electron here, you might have an electron here. These are electrons. So the distance between the nucleus and this nucleus, I'll call that D, is different than this distance here. I'll call this D1 and D2, and that's different than this distance here, D3. So each of those electrons has a different potential energy, V1, V2, and V3. And that's something that we're interested in, right? Because we want to understand what the atom is made up of and how it behaves. So the distance of the electron from the nucleus is important for figuring out that distance. So the potential energy of the Earth and the Moon is different now than it used to be because the Moon used to be closer. Over time, the Moon is moving further and further away from the Earth. If you had been around a couple billion years ago, the Moon would be very large. It'd be twice the size of the Sun in terms of your vision, right? In a couple billion years, the Moon will be further away from the Earth, and it'll appear smaller. It won't be as nice to look at on a full moon. It'll just look like a little smaller ball. So the potential energy is changing as the Moon moves further and further away. The potential energy is actually different, okay? So that's potential energy. Now, what is kinetic energy? Kinetic energy, I said, is something you can generally see. You can see it in action. An explosion shows you, things are moving, right? So kinetic energy is about movement. This is all about movement. Something is moving, okay? So what we would say is that in general, so I'm going to use a K for kinetic energy. So V for potential energy, K for kinetic energy. The faster something moves, the more kinetic energy it has. So as the speed increases, the kinetic energy increases. As the mass increases, the kinetic energy increases. And we'll look at that. We'll calculate that later in the chapter. Actually, I think we do it in the next chapter. So it turns out kinetic energy, speed affects how much kinetic energy something has, faster, more, and the mass also does. So the more mass something has, the more kinetic energy it has. Okay, so there's a typical, there's a problem in your ALEX homework where they ask you to essentially look at a diagram. Okay, I drew this kind of crude diagram, and essentially what you do is you have this little bicycle here, and there's someone riding on the bicycle. Okay, and they ask you to kind of go through this path and talk about potential and kinetic energy. Okay, and this is talking about gravity here. This is not talking about electricity. When you ride on a bicycle, you're not worried about electrical energy. You're not worried about electrical potential energy. You're not an electron that's moving around a proton or nucleus. You're essentially moving up and down hills. And so that's about gravity, right? So what we know about gravity is that if you go down a hill, you speed up as you're going down the hill, right? So you go faster as you move down the hill till you reach the minimum. And once you reach the minimum, that's when you're going the fastest, right? And then you slow down as you go up the hill. So now you're going the slowest. And then you go faster again. And then you go slower again. And then you go faster again. So here you're at your fastest point right there, right? and then slower. Right there. And that's essentially what's going on. So here's the relationship. When you're going the fastest, you have the most kinetic energy. So this would be a large K when you're down here, right at that minute. That's where you max out your kinetic energy. And then when you're going the slowest, which would be the top of the hill, this would be a small K. Your kinetic energy's gotten small. And then again, once you get down to here, you're going the fastest, you have a large K, large kinetic energy. And then when you get up to here, you would have a small K. And then again, down here, you'd have a large K. Okay, so when you reach the minimum, that's when you have your large kinetic energies. When you reach the peaks, right? The peaks are where you're going to go the slowest. If you've ridden a bicycle, you know that's the case. If you've ever ridden, run a hill, right? Try running up hills, right? Once you get to the top of the hill, you're going pretty slow. But then once you get down to the bottom hill, you're going pretty fast. Okay, so kinetic energy is going to be associated, large kinetic energies are going to be associated with these minimum points, the troughs. And the small kinetic energies are going to be associated with the peaks, right? So that would be a small K there. Okay, because kinetic energy is associated with speed. Now, what about potential energy? The potential energy is the reverse, essentially. What happens is, if you think about it, if you're going to jump off a very tall mountain, you're going to think about it before you do it, right? You're not moving, right? When you're at the top here, you're not moving, so you don't have any kinetic energy. So why should you be scared? Because inherently, you understand when you were a baby that if you got on a step and you fell down, you got hurt, right? We picked that up very quickly. So we have an intuition about potential energy that we're not born with it. We don't understand potential energy when we're born with it. But after one fall, it really only takes one fall for some, maybe it takes two for other people. After one fall, we realize the significance of potential energy, which is that if we jump off this cliff, we're going to start moving very quickly, right? So we realize inherently that there's potential energy right here. So when you're at these peaks, when you're moving the slowest, right? If you think about it, it's not necessarily intuitive. You're not moving, but you know you have energy, right? This is when you have a large potential energy, is when you're at the peaks. So when you have the smallest amount of kinetic energy, you actually have a large potential energy. So you have large potential energies here. And what about at the bottom? Well, at the bottom, actually, that's when you've essentially lost all of your potential energy. So like if you walk down here and you haven't fallen, so let's say you're just down here, falling down is not a big deal, right? You're not going to get hurt if you fall down. If you're already on the floor, you're not going to get hurt by falling. It's when you're up high that you're going to get hurt, right? So here you have small potential energy. You don't really have any potential energy. So when you can probably see the pattern here, right? When you have the large K is when you have the small v, right? And the reason for that is that your total energy is equal to your kinetic energy plus your potential. And so what happens is when you have a very large amount of potential energy, you don't have any kinetic energy. When you have a large amount of kinetic energy, you don't have any potential energy. And when you're in between, you have a mixture of both, right? So this is often called the work theorem, the energy work theorem, but we often in chemistry call it the conservation of energy. Right? The conservation of energy says that up here you have a lot of potential energy, but no kinetic energy. Down here you have a lot of kinetic energy, but no potential energy. And in between you have both. But you never have more than one number. At no point along this path do you have more than what you started off with. So if you knew how much energy you had right here, you know how much you have the whole path. You never have more than that. You never have less than that. You just have a combination of the kinetic and the potential energy. Okay, so there you go. So that's sort of the first problem. They just ask you to run through all of that. So good luck this week. Tomorrow we'll look at some more examples of energy and start getting into a little bit of the chemistry and how that relates to it. And reach out to me today if you have any questions, and I'll talk to you later.
Thank you, Professor.
Bye-bye.
Thank you.